So Sylvain is a CNRS researcher working in Montpellier, France, on the evolutionary implications of epidemiology of infectious diseases. And I'll hand straight over to you. That's great. I can see your slides. I think you might be muted.
Sorry. Thank you for the invitation to speak today. So I want to speak about the speed of pathogen adaptation. And I want to start with, it's not working, with this paper. This paper was published a little bit more than a year ago, and I think the title really sums up quite well the classical view that pathogen adaptation is a very slow process. At least it's a process that is much slower than the speed of epidemics. So whenever there is an emergence of a new epidemic, we should try to stop the epidemic, control the disease, but worry later about the adaptation of the pathogen. Yet, thanks to the massive sequencing effort that has been carried out in UK, we know from last fall that the SARS-CoV-2 is a virus that evolves and can adapt to the human population. And in fact, the distribution, the transmission of very highly transmissible new variants is actually challenging all the control efforts that have been carried out in many countries. So this is worrying. This is also a big surprise, given what we knew from the evolutionary speed of pathogens before. So what I want to discuss today is to try to use theory to see whether we can think clearly about the speed of adaptation, and in particular in the adaptation to vaccines. So of course, when we think of vaccination, we're hoping that vaccines are going to be perfect, so they will completely prevent infection by the disease. But we know that most vaccines are actually imperfect. So after being immunized, the host can still be infected by the pathogen. So this has obvious epidemiological consequences, because with imperfect vaccines, you need to vaccinate a larger fraction of the population to control the disease and hope to eradicate the disease. But there are also evolutionary consequences of this imperfect vaccination. So that's what we've been studying in these papers almost 20 years ago now, showing that imperfect immunity is creating an heterogeneity in the host population. So now the pathogen is facing a variable environment where some hosts are naive. The immune system is quite is not primed by the vaccine, and then there are other hosts that are immunized, where the immune system is cranked up, and this may select for different evolutionary strategies, different life history strategies in immunized hosts. So in these previous studies, what we showed is that different types of vaccines may select for different life history strategies. For example, vaccines that may decrease the growth rate of the parasite within the host may favor more virulent and transmissible strains. But those models were meant to describe the long-term evolutionary dynamics of the disease. So they are quite useless to think and to discuss the speed of adaptation. So that's what I want to discuss next. And I will follow the steps of pathogen adaptation. So we'll start with discussing mutation. Are there any adaptive mutations in this virus? Are these mutations able to invade? So following up from the talk of Robin, it's really the early step of the emergence. Are they going to escape early extinction? And if they manage to escape extinction, I want to use deterministic models to look at the single locus and multi-locus evolution of the pathogens. So throughout the presentation, I'm going to use very simple models. So very unlike the models, the sophisticated models that have been used to model, to predict the spread of SARS-CoV-2 epidemic. The idea is to use very simple toy models to try to think about the factors that may affect the speed of adaptation. So we're going to assume that susceptible hosts can become infected at some rate, which depends on the transmission rate of different genotypes. So the subscript I refers to the strain of the parasite. And infected hosts may either die from the infection, and virulence is going to measure the ability of some strains to cause disease and kill the host. And hopefully the host can recover and become immune. And vaccination may happen either during the birth, just after birth, or it may also happen for adult hosts. And this will lead to heterogeneity in the host population. Some hosts will become immune, vaccinated by the vaccine. And this imperfect vaccine will confer some immunity. And we're going to assume that immunity may affect different steps of the infection process. For example, this parameter ρ1 is going to limit the probability to become infected. ρ2 is going to decrease the growth rate of the parasite inside vaccinated host. And it will also affect the transmission rate, because the growth rate will lead to higher transmission. ρ3 is a parameter that decreases transmission without affecting virulence. ρ4 is a parameter that affects virulence without affecting transmission. And finally, ρ5 is a parameter that increases the recovery rate of vaccinated hosts. So first, mutation. Is mutation limiting in SARS-CoV-2? So the good news is that the estimation of mutation rate of SARS-CoV-2 give an estimate of mutation rate that is much lower than other viral pathogens of human population. So this is a good news, because we know that vaccine effectiveness is related to the ability of a parasite to escape immunity through adaptive mutation. So, for example, we know that vaccine effectiveness against influenza is pretty low, because influenza virus has a high mutation rate. Yet, we also know that some mutations have been described to be able to escape antibody response. So it's unclear whether the current vaccines that are being used are actually going to be escaped by the SARS-CoV-2. But for the following of the talk, I'm going to assume that those mutations, there is phenotypic variation on escape, on the ability to escape immunity. And what I'm going to look at next is whether those mutations are going to escape early extinction. So this is the work of Todd Parsons in collaboration with Amaury Lambert and Troy Day. And for this part, we're going to use a slightly simpler version of the model. Again, there is a fraction of the population that can be immunized. And now the adaptation is going to allow the parasite to escape immunity by the vaccine. So this parameter E is going to affect the ability of the parasite to escape immunity. And the different mutants may also have different life history traits like transmission and virulence. So this is the model that we can use. So this is a deterministic model to follow the epidemiology and the evolution of the system. So we can track, for example, the density of naive hosts infected by the wild type and the mutants, but also the density of vaccinated hosts infected by the wild type or the mutant. But for this talk, I'm going to focus only on the frequency of the mutation, which is defined here. And we know from population genetics that the change in frequency of the mutants is a function of the genetic variance of the mutation in the population times the selection coefficient. And this model, the selection coefficient, is simply the difference between the Malthusian growth rate of the mutant and the wild type. So the Malthusian growth rate is a function of the life history traits. So it's basically this first term here describes the production of new infections, which depends on the transmission rate of the variant I, but also on the availability of susceptible hosts in the population. And this term here describes all the parameters that are going to decrease the number of infections, either by mutation, by death, or by virulence. And I want to note here that this is the relevant measure of fitness in this particular model, and it's quite different from the effective reproduction number that is often estimated in an epidemiological model. So as we will see in the next few slides, it's very important to be very careful about the relevant measures of fitness. So this slide is meant to describe different outcomes that may occur after the start of vaccination. So each panel describes one possible scenario. So we start in each case with some endemic infection. In the blue area, we start using a vaccine against the disease. So the density of infection is going to drop. And eventually it may reach an area where the density is so low that it will be subject to demographic stochasticity, and it could lead to extinction of the disease. So in this first panel, vaccination leads to eradication. So it's a successful control of the disease. But if the vaccine is imperfect or the coverage is not high enough, it is very likely that it will be difficult to eradicate the disease. So it will lead to a new endemic equilibrium after some damped oscillations. And here there is plenty of time for escape variant, new mutant to arise. And what we're going to look at in the other situations is what happened when an adaptive mutation emerges in the population, in the pathogen population. So first case may occur where the mutation emerges but fails to invade the population. So it will remain in this danger zone where stochasticity is very high. So the mutant may go extinct very rapidly in this case. And in this second situation, the mutant manages to escape extinction. It reaches a very high density, but in such a scenario, the epidemiology is so high, so that it leads to such a high epidemic that it will lead to a drop in the number of infected hosts and back to the danger zone where extinction may occur again. So in this case, invasion is unsuccessful because it will lead to extinction of the mutant. And then other situations, we can also find situations where the mutant invades and coexists with the wild type for some time, or it can actually outcompete the wild type and lead to fixation. So next, I want to show a few slides about a numerical example where we use a situation where the wild type is unable to escape immunity. So this parameter E is equal to 0. The mutant, in contrast, is able to escape fully the vaccine effects. But note that there is a cost of this escape mutation. So the transmission is much lower than the wild type, which leads to a basic reproduction ratio, which is lower for the escape mutation. So before vaccination, the wild type cannot be outcompeted by the mutant. Yet after vaccination, the wild type will reach a new endemic equilibrium where the effective reproduction number will be equal to 1. But because the mutant is able to escape immunity of the vaccine, its effective reproduction number is higher. So after vaccination, we expect the mutant to be able to invade the wild type. So here I'm going to plot the probability of invasion of the mutant as a function of the time of introduction of the mutant. So unlike, I think, what Robin presented here, we're going to control the time at which the mutant is introduced. So it's not going to be generated by the resident population. We introduce the mutant at some point in time, and we can compute this probability of invasion. And in fact, there is a very simple result. If the mutant is introduced very late after the introduction of the vaccine, the population will have reached a new endemic equilibrium. And in this case, the probability invasion is simply a function of the ratio of effective reproduction number. Okay, so in this case, 1/2. But if the mutant is introduced sooner, then we need to use a classical result from Kendall, because what is going on here to describe the invasion of the mutants is that we have to use a branching process model where the mutant basically can produce new infection. So this is a birth rate, which is given here, and it can die at some rate here. And what is important to notice here is that the birth rate is going to change through time, okay? Because the birth rate is a function of the density of susceptible hosts in the population, and this density is fluctuating through time. And for example, the number of vaccinated susceptible hosts is going to increase through time. So if you compute this quantity, the probability of invasion, you obtain this curve. So early on, just after the start of the vaccination, it's very unlikely that the escape mutant will invade, but this probability will increase and reach this quantity. So next, I want to show another scenario where we're going to use another escape mutant. And the only difference here is that it will have different life history traits. Okay, so this red mutant has a higher transmission rate and higher virulence than the green one. So which means that the per capita growth rate is higher for the red than for the green. Yet they both have the same effective reproduction number. And in spite of this red mutant to have a higher deterministic fitness, we notice that the probability of invasion is lower. Okay, and the reason for that is that this life history lead to much more variance, and therefore it's much more riskier for the red mutant to invade, because there is a higher risk of extinction because of this very high virulence associated to this mutation. Okay, so the probability of invasion is lower for the red mutant. So next, we may wonder what happens after invasion. So in the green case, for the green variant, invasion always leads to fixation. So the mutant will outcompete the wild type and will reach fixation. Whereas for the red variant, it is very unlikely to go to fixation. So the mutant may invade, but soon after its invasion, it will go down in density and it will go to extinction. So if we go back to this graph here, what is going on here is that the red mutant is actually a good illustration of this panel, where the mutant can actually manage to escape early extinction, invade, but because it's a very highly transmissible strain, it creates massive epidemic and then a massive drop in the density of infected hosts, which leads to extinction. In contrast, the much slower variant is living a less risky life, and it will lead to the outcome that the slow mutant will avoid this extinction zone and manage to outcompete the wild type and lead to fixation. So the bottom line here is that life history matters. So not only the effective reproduction number, which are the same for the red and the green, but life history traits matter. So now I'm going to go into what happens after invasion in the so we can use deterministic models to look at that. And again, life history matter a lot. So I'm not going to talk too much about that because I think Troy Day is going to discuss that tomorrow. I just want to present an analysis that we've been carrying out with Sébastien Lyon, which was actually inspired by a talk that was given by Julia Gog a few weeks ago in the Juniper video conference that she gave. And she looked at a situation where there was some heterogeneity in the host population. So unlike in the previous model where all the hosts were the same, except for the vaccination, here we're going to assume that there is a fraction of the hosts which is more prudent than another fraction of the hosts where transmission may be much higher in these hosts than in these ones. So those are the low transmission hosts, and those are the high transmission hosts. And this parameter n controls the amount of transmission that is occurring when you're a high transmission host. And so here we consider a vaccine that affects the row 1 and row 3. So it's going to limit infection and it's going to limit also transmission. And we're going to consider the speed at which an escape mutation may spread in those populations. So again, we can go back to this simple expression for the change in frequency of the mutant. And it's possible to write down the selection coefficient. So I won't go into the details of this equation. I just want to notice that this expression depends on those V terms which actually measure the reproductive values of different types of hosts. Okay, so in this heterogeneous host population, there are different types of hosts, and they are associated with a reproductive value which measures the quality of the host from the point of view of the pathogen. Okay, So there are naive hosts that are with low transmission, vaccinated hosts with low transmission, and the same with high transmission hosts. So we can use these equations to follow the evolution of the mutation, but we can also use some approximations. So for example, if we assume that the effect of the mutations are weak, there is a separation of timescale argument that allows us to derive an approximation for the ratio of reproductive values, which is quite useful because then we can write down the selection coefficient as a function of these three terms. So the first term is the mutation effect. The second term depends on vaccine efficacy, and the last term is really depending on the density of the different types of hosts in the population. So this is interesting because I think what Julia Gog was after in her talk was to see whether if we use targeted vaccination, so for example, we can target only low transmission hosts or high transmission hosts, we can look at what are the consequences for the speed of evolution. So indeed, so those are the results of this approximation, dotted line, and the full line are the numerical simulations. And indeed, if we vaccinate only low transmission hosts, we see that the increase of the mutation is smaller than if we vaccinate only highly transmitting hosts. And this is due to this M factor here, which measures again the increased transmission of those big hash hosts. Okay, so these tools may be useful to try to better understand what are the consequences of targeted vaccination on the speed of adaptation. And finally, if I have some time, I can talk about yet another project with Dave McLeod, where we've been interested in looking at multi-locus evolution. So here, we go back to the general model. And here we're going to assume that there are two locus involved in adaptation to the vaccine. So in the first locus, we are going to assume that there are two alleles. One allele may be an escape mutation that can escape the effect of immunity. And then the second allele is going to affect the life history of the trait. So in particular, the big V allele is going to increase transmission and virulence, which is yet another way to adapt to the effect of the vaccine. So in this case, there are four different genotypes. And we can look at the evolution at the two locus. So we can again recover these equations if the frequency of the mutations are independent in the two locus. But we also know that maybe some epistasis in fitness may occur. So this will affect the change in frequency because, for example, two alleles work very well together. It will affect the change in frequency of the focal allele. And also, if there is genetic linkage between the locus, we know that selection on one allele, for example, the V allele, may have an effect on the change in frequency of the E allele. So we can also write down dynamical equations for the linkage equilibrium. So I won't go too much in the detail. I just want to show that actually different vaccines can have a different impact on the epistasis, on the sign of epistasis. In particular, if we use a vaccine that increases Rho2, so that decreases the growth rate or Rho4 effect, this will lead to negative epistasis. So with negative epistasis, the prediction is that the pathogen will evolve to two different strategies, either evolve towards escape mutation or in contrast to the virulence adaptation. So those trajectories are issued from random simulations where they've picked different parameter values. So we see that some trajectories lead to this fitness optima or other trajectories to this one. And when we increase recombination, it will prevent the linkage equilibrium to build up, and it affects the dynamics. And we see that, for example, some of the trajectories are going to be trapped at the local fitness optimum because recombination blocks access to the higher fitness peak in this situation. I don't have time to discuss other scenarios, but in this case, we noticed that if we use other vaccines, we can generate positive epistasis, which is actually quite worrying because you could evolve the accumulation towards the evolution of a combination of both the big E and the big V allele. just to wrap up about adaptation of SARS-CoV-2, I just want to say that maybe we are reaching the end of the phase 1, which happened before vaccination. And in this phase, there is selection for a higher transmission rate. I mean, the models that I've been showing can be used to show that selection for higher transmission is driven by the availability of susceptible hosts in the population. I think Troy is going to discuss about that tomorrow. And now we are entering a new phase, a phase where vaccination is going to increase the density of course, immunized hosts, and this will select for escape mutants. So I hope maybe some of those models may be useful to figure out what are the consequences of different vaccination strategies on the speed of adaptation. So I'm going to end here, and I will thank my collaborators, and in particular Todd, Sébastien, and Dave for the earlier, the last project that I presented today. Thank you.
Many thanks. It's a really useful framework and a great start to the more detailed scientific discussions. I'm going to take this two questions in the Q&A box. So I'll read the first one, which is from Andre. Thank you for the interesting talks. There were some reports of a narrow transmission bottleneck for SARS-CoV-2, so low heterogeneity in between host transmissions, when, for example, compared to influenza. I'm wondering naively, could some complementary mutations or some other biological factors widen the transmission bottleneck, making the virus more similar to influenza, making the virus escape more likely? That's a nice, tough one to start on.
Yeah, so unlike what Robin talked about, I really use models here that focus on between host transmission and not so much about within host dynamics. So I guess this question is about the diversity that may occur within a host, and these bottlenecks may actually reduce variation from one host to the next. And of course, this is very important to fuel adaptation. And I'm afraid, I mean, these kinds of models I presented, I have little to say about that because I'm modeling the transmission between hosts.
We may call on Robin or even Claudia to also help you answer that one. Thank you. But I think it'll be a subject for discussion later. A question, I think, more specifically for you from Ben. How feasible would it be to extend these models to stochastic versions?
Okay, so the first part of my talks were about stochastic models. So maybe that was not very clear, but the talk, and particularly the work by Todd Parson, is really in this part. We are really interested in the early stages of the epidemic, where the escape mutation is at a very small number. Because the number is very, very low, it means that there is a very high risk of extinction. And to model that, we can use a birth death process to figure out the risk of extinction, and that's precisely what we've been doing here.
Thank you. Troy was asking where the Q&A is, but because he's a panelist, he can actually ask his question. If you want to ask Troy your question, and then Juliet also has the question in the...
I'll ask it verbally if that's okay.
Yep, that's fine.
Hi, Sylvain. Nice talk. I was wondering, in the very last stuff you talked about there with recombination, was the rate of recombination, it's presumably linked to the force of infection as well. I assume that was the case in the model. And if so, how are you controlling what the rate of recombination was in those two different scenarios?
So there are two parameters hidden here. There is the actual recombination rate when there is a co-infection between two parasites, and there is also the rate at which co-infection occur in the first place. So I guess there is a single parameter that controls both in this case. And the point here was really to describe qualitatively what happens when there is no recombination at all, which means that linkage disequilibrium can build up. And a situation where there is some recombination, which will prevent recombination and will be preventing the pathogen to explore the whole fitness landscape because of the influence of recombination. But indeed, there is an impact of epidemiology on the rate of recombination.
Okay, yeah, because I was wondering if so you could imagine NPIs and things like that would then affect the rate of recombination and so potentially affect what happens evolutionarily too. Interventions that reduce the force of infection.
Yeah, that's right. Yeah. So if there, so again, something that I didn't mention also in all those models, there's no control measures on top of vaccination. So indeed, you're right. So if we would apply some control measures that would lower the prevalence of the infection, it could have an effect on recombination and maybe go from this part to this part. So there will be an evolutionary implications of those interventions.
Thanks.
So we're running slightly into coffee, but I think, Julia, if you want to ask your question, I just note for everybody, Katrina Lithgow's put a response about the bottlenecks in the chat, which would also be useful for later. Julia, go ahead.
Thank you. Marvellous talk, Sylvain. Thank you. I like the two phases thinking very much, but the thing that moves you between them is vaccination and thinking internationally. We've got this really heterogeneous picture now where some places have moderate to high coverage and some have none. What does it mean if different countries are in different phases now for global evolutionary dynamics?
I guess I mean if you go back to the models, okay, can you do that? You don't see my screen. What is very clear from the analysis of the selection, it really depends on the density of vaccinated hosts in the population. So I guess that if vaccination is much higher, then you expect the selection to be much higher in some countries than in others. So I guess the prediction from that would be that the adaptation would be faster in some countries than others. So if we want to project ourselves in a few months, I would say that those countries that increase the high rate of vaccination will have a higher risk of seeing the escape variants occurring in those populations. So, I mean, ideally, I guess we would like all the countries to apply vaccination at the same time, so it would have a massive effect on the density of the pathogen population, the prevalence of the pathogen populations, because as Robin pointed out in his talk, if you have a lower number of pathogens, then there is a lower input of mutation in the first place. I'm worried that if we have a heterogeneity in the speed at which countries vaccinate hosts, this may actually be quite harmful because there will be a lot of mutation input coming from countries that have not yet vaccinated the population. So I'm not sure I answered the question or if it's exactly the question that you answered, but yeah.
No, you confirm my worries. Thank you. Yeah. Thanks. There's some points we can come back to in discussion tomorrow if we have time, but that's great. Thank you.
Yes, absolutely. It is technically now coffee time for half an hour. So I'll hand over to the chairs for the afternoon. But thank you very much, speakers, so far this afternoon or this morning, depending on which time zone you're in. And do feel free to continue the conversation, panelists, verbally or in the chat. And the next talk will be at 12:30. Thank you very much.